A single lightning strike holds enough energy to turn the air into plasma. It is raw, violent, and represents electricity in its most chaotic state. Contrast that with the connection point of a smartphone charger. Here, that same physical force is delivered with such precision that it can power a microscopic processor without melting the plastic casing. This safety is the result of a constant physical tension. Electricity naturally seeks to discharge all its stored potential as fast as physics allows. Left unregulated, that discharge would instantly incinerate every piece of technology you own. In 1827, German physicist Georg Ohm identified the specific mathematical rule that makes this level of regulation possible. He transformed electricity from a terrifying natural phenomenon into a predictable engineering tool. We have learned that harnessing power is only half the battle. The real work is control, and Ohm's law is the universal instruction manual for that control. To see how this manual works, we have to isolate the three specific forces that dictate how electricity moves through a circuit. Physicists often visualize these invisible forces as water flowing through a pipe. By mapping electrical variables onto this plumbing system, the math becomes a tangible physical interaction. First, there is voltage, measured in volts. In our pipe, voltage is the mechanical pump. It is the electrical pressure, the push, that drives the entire system forward. Next is current, measured in amperes. Current is the actual volume of water moving past a specific point. It represents how many electrons are actually flowing through the conductor at any given moment. Finally, we have resistance, measured in ohms. See how the narrowed pipe restricts the water's path? Resistance is the material's physical opposition to that flow. Every physical material, from copper wire to the heating element in your toaster, has some degree of internal resistance. In the electrical world, no flow is ever perfectly frictionless. Every circuit is a locked, dynamic ecosystem. The push, the flow, and the friction are in a constant, unavoidable state of interaction. George Ohm proved that this interaction follows a rigid mathematical ratio. He locked these variables together in a single, elegant equation. This triangle represents the equation: voltage equals current multiplied by resistance. Because these variables are mathematically locked, changing one forces the others to react. If we increase the voltage, the pressure, while keeping resistance the same, current must increase proportionally to maintain balance. This is why hooking up a larger, more powerful battery naturally results in a stronger, more dangerous rush of electrons. Conversely, if we increase the resistance, the friction, the current is squeezed down. The higher the resistance, the slower the flow. This allows us to reduce a dangerous current without ever changing the battery. We can simply increase the physical resistance of the wire to throttle the flow. Engineers use this triangle to calculate exactly how much friction they need. By dividing voltage by current, they can determine the precise resistance required for a circuit to operate safely. This equation grants us predictive power. We can dictate exactly how electricity will behave before we ever connect a physical wire. Consider a common problem. You need to power a delicate LED light using a 9-volt battery. Direct current from a 9-volt battery provides far more pressure than a tiny LED can handle. Without intervention, a 9-volt push forces a massive surge of current into the bulb. The LED flashes once and shatters, destroyed by unregulated heat. To save the light, we use Ohm's law. We take our 9 volts and our target current and calculate the exact resistance needed to throttle that surge. We then install a physical component called a resistor, represented in schematics by this zigzag line. These act as the brakes of the circuit, absorbing the excess voltage as heat, slowing electrons down so they reach the LED at a safe, functional speed. From the microscopic chips in your smartphone to these massive high-voltage power lines, Ohm's law is the invisible framework that keeps our modern world reliable and safe.